Suppose that we actually want to do something useful with our finite state automata. Let's say, for instance, we want to add together two numbers in base 10. Remember that finite state automata don't know anything about numbers. They only know about strings of symbols. So when we want to input a number, we need to encode it in some way. And we can just use the standard base 10 encoding, and we can input the number as a string of symbols from the character set, from the alphabet of characters from 0 to 9. But right away, we run into an obstacle. Finite state automata can only output a single bit, accept or reject, yes or no. This input is good or this input is not good. And when we're trying to calculate a function, an operation, like addition, we're looking for a full number as output, a full string of digits as output. So that's no good. But the process of encoding functions as relations, as predicates, as things that take in some input and just output true or false is a fairly common process in logic and particularly in set theory. So for instance, instead of encoding the function that we want as taking in two inputs and outputting their sum, we can view this as a relation that takes in three inputs, the inputs to the original function and a proposed output. And this is going to be true if that actually is the output for these given inputs. And with respect to logic, we don't lose anything here when we do this translation, because if we wanted to say something about f of ab, say that it had some properties, all we would have to do is say that there exists some c such that r of abc, and then c satisfies those properties. So in terms of first order logic, we haven't lost anything by doing this translation. This is a perfectly acceptable way of capturing addition. So let's kind of do the naive thing here. Let's say that our alphabet is the set of digits from 0 to 9, along with the character plus and the character equals. And we're going to try to build an automaton that accepts words that are just of the form a plus b is equal to c, where a, b, and c are the encodings of numbers, and it has to actually be the case that a plus b is equal to c. So for instance, we're going to want our automaton to look at the string 1, 2 plus 3, 4, 5 equals sign 3, 5, 7, right? This is just a string of symbols. We want our finite state automaton to look at this string of symbols and accept it. But there's a small problem here. It's perfectly fine to build an automaton that checks to see if we have some string of digits, followed by a plus sign, followed by some string of digits, followed by an equal sign, followed by some string of digits. That's perfectly fine. A finite state automaton can just keep track of, do we think we're in this part of the input, or this part of the input, or this part of the input? And if we see something unexpected, then we fail, and if not, we accept. So that's perfectly fine, but actually doing the calculation, we need to store these numbers somehow in memory as we read them in. In particular, once we've finished reading this first input, once we encounter this plus sign here, we need to have in memory this entire number. And when we encounter this equals sign, we can maybe have done our calculations already as we were going through. As we read the second number here, we can start doing some of our calculations and throw out some of the information. But when we encounter this equal sign, we at the very least need to have in our memory the output number so that we can compare whether or not the thing that we're about to see is the correct output number. So at this point, we need to have enough memory to store this number, and at this point, we need to have enough memory to store this number. And the issue here is that if we really wanted to capture true addition, not computer scientists' addition where integers only go up to 4.3 billion, but actual mathematical addition where the inputs can be as large as we want, then we're going to need unbounded memory. We're going to need enough memory to store whatever integer comes our way in the first part of the input. And that's not what finite state automata do. Finite state automata only have a limited amount of memory. It could be a lot of memory, but there's always going to be numbers that are larger than that bounded memory. So we actually can't construct a finite state automaton that reads in inputs that looks like this and captures whether or not these are true addition statements. Forget about if we wanted to, for instance, capture more complicated statements involving addition, like maybe add 3 things together and it's equal to the sum of 2 things. We can't even recognize when we have the sum of 2 things is equal to a third thing when we input it like this. So how could we input this stuff into a finite state automaton so that the automaton can actually do addition, can actually determine whether or not a plus b is equal to c? Well, let's think about this. When you're adding together 2 numbers, when you're checking your work, when you do addition, all you need to do is look at all of the ones digits at the same time and check to see if they're compatible with each other. And then you have to remember the carry digit, so that's a piece of information that you store from one input to the next, state, as it were. And then you look at the tens digits, and you check to make sure, given the carry bit that you've remembered, is this sum okay? And then you look at the hundredths digits. This could get a little bit tricky. There is no hundredths digit here, so maybe we want to toss on a hundredths digit here. And then you check the hundredths digits and make sure that they're consistent with each other and with the carry bit that you remember, and so on and so forth. So what we want to do is we want to set this problem up in some way so that we can look at the ones digits all at once. And so the way that we're going to do this is we're actually going to plug 3 keyboards into our finite state automaton, and on the first keyboard we're going to enter the first number, and simultaneously on the second keyboard we're going to enter the second number, and on the third keyboard we're going to enter the third number. So what this is going to look like, and I'm going to write it this way, but we're actually going to want to read it this way. Remember that when you're actually doing addition, you want to start at the ones digits and work your way up. It turns out this doesn't actually matter for the purposes of constructing finite state automata. You could, instead of remembering the carry digit, you could try to anticipate the carry digit, and if you're wrong, then you say, something is broken, and then go to a failure state. What we've done here is we've constructed a new alphabet, where each of the characters in this new alphabet is simply a triple, a vector of 3 characters from the original alphabet, from the original digits 0 through 9. And the key thing here is that this new alphabet is finite. There are only 1,000 different possible symbols within this alphabet. So large alphabet, but finite alphabet, and that's the important part. Notice also that we've had to pad this first input with a 0 here in order to get them all to be the same length in order to be able to do this construction. And this is standard. This is something that you always have to do. In this case, we have a special pad character 0, but in the general case, you're going to have to add in a new padding character to pad your inputs to distinguish it from characters that you already have, and pad all of your inputs so that they're all the same length before you can do this kind of vector construction of a new higher alphabet. So it should be clear at this point how to turn this into a finite state automaton. We only have to keep track of 2 pieces of information. We need to keep track of the carry bit so we can keep track of carrying from one place to another, and then we also need to keep track of whether or not what we're looking at is correct. If we notice at any point in reading our sum that there's an error in our calculation, then we go into a failure state and we say we cannot escape this failure state. So we know not to accept if at any point we see an error, and if at no point we see an error, then that's fine. We are correct. We have seen a correct summation. I'll give you a moment if you want to figure out how to present this finite state automaton, and then I'll show you how to do it. So here we have our specification. We have our alphabet, which is going to be vectors of characters from 0 to 9. We have our set of states. Here we have a carry bit of 0, carry bit of 1, and an error state if we've seen something go wrong with our summation. Our start state is 0. We start off by not carrying anything. If we have a carry bit of 0 and we see an ijk, this is going to be okay, and we're going to carry a 0 if I plus j is equal to k. Otherwise, if I plus j is equal to 10 plus k, we're going to carry a 1. And otherwise, this is no good. We're going to go into the error state. And similarly, if we see a carry bit of 1, we're just going to add a 1 here when we check these additions. And if we're in an error state, we stay in the error state. We cannot escape the error state. And then finally, our set of except states, our final states, is going to be just 0. If we're still carrying a 1, we're going to have to deal with that 1. But if we're just carrying a 0, we don't have to deal with that 0, and so we can accept once we see that. And again, it's important to note that this finite state automaton, when we're actually using it to reason about addition, we have to kind of tuple our inputs together, and we also have to read them from the ones digits upward. So let's spell out explicitly what we've done. We've taken our inputs and we've padded them to all be the same length, and we're reading in our inputs simultaneously. We're reading in the first characters of all of the inputs, and then we're reading in the second characters of all of the inputs, and then the third characters of all of the inputs, and so on and so forth. So we can generalize this to any sort of problem that we want to address with finite state automata. So we say that a relation is regular if there is some finite state automaton M such that R of these inputs, if and only if M accepts these inputs when we have padded them to all be the same length with a special padding character. I like to indicate the padding character with an octothorpe, just because this tends not to show up in other alphabets that we construct when we're doing applications. And the key thing is that this padding character really shouldn't be any character that is in our alphabet. It should be a new character that we're adding to the alphabet in order to pad in a way that's unambiguous. This tupling operation, the first character of the tuple of these inputs is going to be the tuple of first characters of all of the inputs. And the second character of our tupled inputs is going to be the tuple of second characters of all of our inputs, and so on and so forth. Exactly like we did with the addition. So let's do another example. Let's take a look at the prefix relation. We say that x and y are words. X is a prefix of y. And we use this kind of curly less than or equal to sign. Notice the equal to, so that x could be equal to y. They could be the same word. We say that x is a prefix of y if y is just x, possibly with some more characters tacked on to the end. So for instance, x, if x is the empty word, if it doesn't have any characters in it, then every word is going to be an extension of it. The empty word is a prefix of every word. This is a very important relation within the context of abstract languages here, and it also happens to be regular. So if you want to, pause the video and take a moment to try to work out what the corresponding finite state automaton for this relation looks like. And to get you started, let me show you an example of inputs that are going to be accepted. Let's say that we wanted to say that the word ABBA is a prefix of ABBAAB. Then we would need our finite state automaton to accept the inputs. So the alphabet is going to be some extension of the set of pairs of characters from the alphabet, and then it's going to have to recognize something like this. Well, it turns out that this is super straightforward. All we need are two states. We need everything is going okay state, and we've seen something that we don't like state. And once we're in the we've seen something that we don't like state, we are stuck in a loop of failure. We're never allowed back into the accept state. And of course, we start in the accept state. We haven't seen anything we don't like yet. And so if we see an AA, we're happy. If we see a BB, we're happy. If we see an octothorpe A, we're happy. And if we see an octothorpe B, we're happy. Notice that octothorpe never happens. We're only padding up to the length of the longest input. I guess we could pad more if we wanted to, but let's not worry about that. And then, of course, if we see anything else, if we see an AB or a BA, we're going to want to go into the failure state. And then anything is going to take us from the failure state to itself. If we're in the failure state and we see something, we're going to stay in the failure state. So this is our finite state automaton. This is all you need to do in order to show that this prefix relation here is regular, and that will turn out to actually be really important later on down the line. There's actually another way of handling the fact that we want these relations to be able to accept inputs of different length. And that is, instead of padding the inputs to be all the same length, the length of the longest input, because that's kind of a tricky thing to do, we're going to have to do, it's a substantial amount of pre-processing. We could instead think about this if we padded all of our inputs to be infinitely long. So I'm going to define a trailing automaton, which is just going to be a standard finite state automaton, except the alphabet has a special end of string symbol that's only allowed to occur after the end of a string. It's not allowed to occur within the string, and it's supposed to occur infinitely at the end of a string. The input must be finite. It must be a finite string of characters from the rest of the alphabet, followed by this special end of word character infinitely. We're not allowed to use these automata to input infinitely long words. That's something else that's called a Buki automaton. We'll get to it later. So this finite state automaton is going to read the input character by character, and that's going to change what state it's in, and then eventually it's going to reach this infinite sequence of end of string characters, and that's going to put it into, well, eventually it's going to put it into a loop of states. And we have a choice here. I've completely made up the term trailing automaton here, so we have a choice as to how we want to say that this automaton determines what to accept and what to reject. We could, of course, say that it has to be in an accept state going into this this infinite tail of end of string characters. But that's just the same as if those end of string characters weren't there and we just were dealing with ordinary finite state automata. We could also say it accepts if you are ever in an accept state within this infinite sequence of end of string characters. So it could be the case that this thing finishes reading the string and then it keeps going a little bit. And at some point in that process where it's keeping going, it decides to enter the accept state. And then you would say, oh yes, that's perfectly fine. I'm perfectly happy with that. And it turns out that this choice really doesn't matter in terms of what we decide to be a regular language or not. We could just say, if we have an automaton that looks like this, we could turn it into an automaton of the first form by simply saying, we're going to expand the accept states to include anything where if you read a whole bunch of octothorpes afterwards, you would wind up going into an accept state at some point. And so therefore, all of the states that wind up doing this when you read this wind up being declared accept states when you translate it upwards into this type of automaton. And so this type of automaton will accept them immediately when going into this octothorpe sequence. And there's other equivalents as well. You could say, for instance, if you ever wind up in an infinite number of accept states within this thing, or if you eventually wind up in an accept state and stay in the accept state, they're all things that can be translated into this type of trailing automaton. So, and this is really just secretly a standard finite state automaton. So just like how if you made a bunch of small changes to a programming language, you would affect what programs did, but you probably wouldn't affect what your programming language is capable of doing. Again, if we make some slight changes into our definition of what it means to be a finite state automaton, we change what gets accepted and what doesn't get accepted for any one particular automaton. But if we translate, when we update how we think about automata, if we translate our automata from our old programming language to our new programming language, from our old automaton paradigm to our new automaton paradigm, then we don't really change what is and isn't accepted by a finite state automaton. We don't change what is regular and what isn't regular. And this is a really cool thing about finite state automata, which is that we can make changes, we can make some small changes to how they're defined, and we can also make massive changes to how they're defined. And we have something that's exactly as powerful as what we started with. We can use it to do regular language things, and we can't use it to do anything else. So that's it for this video. I hope you learned something, and I hope to see you in a future video.